So I've just released version 4.87 of gpvdm, and the main new features in this are the ability to simulate 2D structures. So previously the model could simulate 1D structures, and this is very good for things like solar cells because they really they're sort of effectively 1D structures with only change the material system in the vertical axis. But to simulate things like transistors and sort of field effect transistors and things like that, you really need a 2D device solver to do this. So I've put this into the model recently, and so this video is really going to demonstrate simulating effectively organic transistors with gpvdm. So as ever, I'm going to demonstrate this on Linux because I use Linux, but the model will run on Windows, and there's a Windows installer there that you can just download, and it'll all work absolutely natively under Windows. So let's start up gpvdm. There it is. So to do simulation of an OFET effectively, so an organic field effect transistor, you click on New and you just select OFET and click Next. And then you need to make a new simulation directory as usual, so I call it simulation, and then click Save. And this is the structure of the transistor that we're going to be simulating. So there's two contacts on the top, so these are aluminums. There's one contact there and one contact there, and I'm going to effectively apply voltage to this contact, and the current's going to flow in and flow out of this contact. It's going to be controlled by a gate. Now this at the bottom, this layer 2, is the gate effectively, and this blue line along here and along here represents effectively insulating the gate, or the gate contact from the rest of the device. And this here is the active layer. I've just chosen a P3HD PCBM active layer, just as a demonstration. It could be any material system. So I'll firstly talk about how to set this structure up. So if you go to the electrical mesh editor here, you can choose whether you do a 1D, 2D or 3D simulation. Currently the model can't do 3D simulation, it can only do 1 or 2D. I might put 3D in maybe next week, but we'll see. So for a solar cell it would be, have a 1D simulation, and you can see effectively you've got a uniform sheet of material there. So if we go back to 2D, and you can see that there's basically 10 mesh points here in the y-axis. So that's down here. There'll be 10 mesh points down there, and there's effectively one mesh point in the x-axis. So it's effectively a 1D simulation. So if you click on 2D, then the number of mesh points in the x direction changes to 10. And what you also see happen with the model is it's basically been split up into a series of sort of bars. Now these bars in red effectively represent mesh points on the electrical mesh, so on the finite difference mesh. So vertically we've got 10 mesh points, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And along here horizontally we've got another 10 mesh points. So that's what these bars represent. And you can change the number of mesh points, so you might want to change it to say 50, hit return, and it'll split it up into 50 individual mesh points there. So I'll put this back to, say, I'll put it back to 10. So clearly the more mesh points you have, the more computational intense it is. The other thing is, so that and this is obviously these are the thicknesses and widths of the device. The other thing that's interesting is the contact. So if we look at I'll just get rid of this. If we look at this contact editor, so I'll get it up again. This is the contact editor, and it basically shows you what happens at various contacts. So if I just maximize this, so you have a better look, you see there's 3 contacts on this device. There's a top contact 2, and the bottom contact, and just pin this to the top. Now. So the first thing we can look at is the start of the contact. So it's got start, this top line represents this contact here. So it's got start as 0, which represents the start of the contact, which is x equals 0. The width, which is how wide it is, and then so that defines basically that contact. Then the second contact is starts at 0.002 meters, and then that's its width there. And then we've set both these contacts to, so it says active contact. These are not active contacts, and I'll explain what that is in a minute. And this little says drop down menu says top or bottom, and this effectively describes whether the contact is on the top of the device or the bottom of the device. So these are on the top of the device, so we've chosen top. Now on the bottom of the device, for this bottom contact, the one in green, we've just defined its width as, you know, whatever the width is. Another interesting feature about this is this depth parameter. So above or below the contact, you can define a passivation depth. So for example, very often just below a contact, you'll add an insulating layer. So you know, this for example here is to stop effectively charge being conducted to this gate pad. So you can change the width or the depth of this passivation layer just by changing this number. So if we change it to 10, you can see it's more of the device is passivated. So we'll change that back to a 5. Now there's this column called active contact. So these two on the top are not active, and the one on the bottom is active. And the active contact effectively defines where so if you do a JV curve, so if you scan a voltage between say 0 volts and 2 volts, it defines to which contact that voltage will be applied. So you can apply it to any contact or any combination of contacts, but it means that you know, if you scan a JV curve, that's the contact that's going to be basically scanned, and it's the same in time domain and all of that. So here, when we run a simulation, we change the gate voltage as a function of time. The final column here is voltage, and this basically defines the voltage or the steady state voltage the contact will be at. So we've got this contact at -1 volt and this contact at 1 volt. So this is at -1 volt and this one's at 0 volts, and so we'll have some type of flow of current between these two contacts. So that really defines or explains the contact header. So the other thing to notice before we set off running this is, if you look in the configure window and look under the solve configuration, to run 2D simulations you need to have Newton 2D in here, which will automatically be in here if you are running an OFET simulation. It will be set up by default, but that's something to check. So let's go ahead and run the simulation. So it's running the simulation. Now this first step that it's doing right now can be a little slow, because it's basically trying to guess the sort of the current and charge profile of the device from scratch. It didn't take very long there, but I might speed that up if there's any demand. So now we've basically simulated a JV curve in this 2D structure, so we can look at the results. So what should we look at? Let's look at the current in the x direction. So if it's Jn x, so Jn x, so that's J is current, N is negative, so that's electrons, and x means in the x direction. So let's have a look at that. So this is the current basically in the x direction at whatever maximum voltage we had on this device, and you can see effectively that there's current flowing on the top of the device, so here basically between these two basically between these two contacts, and then we can go and plot Y voltage and things like that. It's quite interesting to look at this as a function of applied voltage. So if we use the scan window and select Jn x there, we can look at this as a function of voltage. So now we're basically scanning the voltage as a function of time. We can see what's happening, you know, to the flow of current between one contact to the other. We can now go and examine basically the current going through each of the gates, because it's a transistor, and that's an interesting thing to do. So when the number of contacts exceeds 2, so i.e. if you have more than just a top and bottom contact, you get files that are spit out called contact 0, contact 1, contact 2, and so on. So if we go back and look at the contact header, this will be contact 0, this will be contact 1, this will be contact 2. So let's go and plot those. So let's look at contact 2, which is this bottom gate first. So contact 2, let's plot that. And you see basically we've got, you know, very small amounts of current here. So let's keep that on the top and plot the current now going into this contact, which would be contact 0. So let's have a look at contact 0. You can see if you compare the axes, basically very small amount of current coming out of this contact here, and quite a large amount of current coming into this contact. You can see as this voltage is ramped up, and so this one is. So you can see it's definitely having an amplification effect, a transistor effect, by maybe 2 or 3 orders of magnitude. So this is the gate, this is the current going in. We can then plot the current coming out of this contact here. So let's have a little look at that. Contact 1, and can we get them both up at the same time? Oh, let's contact 0. So you see basically here this is current going into this contact, and this is current going out of this contact. And there's a change in sign because one's going in and one's going out because it's a transistor. So that's basically demonstrating a transistor type effect. What else is there to demonstrate about this? I think that's it really. One thing that's worth noting is this button here turns on and off basically dumping of data. So at the moment it's set up with this blue to dump lots of data to hard disk, and there's an SSD in this computer, but if you've got a mechanical hard disk, this can be a slightly slow step. If you turn it off to minimize the amount of data you dump and run the simulation, it'll be much quicker once it gets going. So you see that's actually running quite quickly now. But it'll dump less data, so that's an option worth looking for. This should all run in time domain absolutely fine. If you've got questions about this, please email me. If it doesn't work for you, or you want it slightly changed to do other devices, because I haven't had a great deal of experience doing transistor simulation, so I suspect there's some things I've forgotten to add in here. So if you want some features added, just let me know and I'll be very happy to add them. But that's about it really. So thank you, and I hope this is useful.